All right, let's dive right into this explainer and crack one of the most notoriously tricky topics in IIT JEE mechanics. You know the feeling, right? You see a problem with a spinning disc, a rolling sphere, or a swinging rod, and maybe you instantly feel a little overwhelmed. Well, you are absolutely not alone. But today we're going to fix that. We're going to turn what usually feels like a giant mountain of rote memorization into pure, intuitive understanding. By the time we finish walking through these concepts together, rotational motion is literally going to be one of your strongest assets on exam day.
So here is our game plan. We're going to cover 5 key areas today: the center of mass, torque and angular momentum, moment of inertia explained, linear versus rotational motion, and we'll wrap up with some essential IIT JEE exam tips. We're building your knowledge block by block here.
Kicking things off with Section 1, the center of mass.
Okay, before we can spin anything, we have to figure out exactly where to anchor our physical system. The center of mass is simply that specific point where we can pretend the entire mass of a system is concentrated. Now, why do we even care about this? Well, whether you've got a wildly complex two-particle system tumbling through the air or a massive rigid body, we can completely simplify our math. We can analyze the translational motion of the whole system just by tracking this single concentrated point. It is the ultimate mathematical shortcut.
So how do we actually find it? Think about a two-particle system. The center of mass always shifts toward the heavier particle. For instance, if you have a 2-kilogram mass at the 0-meter mark and a 3-kilogram mass at the 5-meter mark, that center of mass isn't perfectly in the middle, right? It pulls over closer to the 3-meter mark, leaning toward that heavier weight. But if you're dealing with uniform rigid bodies, your standard rods, rings, discs, and spheres, it is beautifully simple. The center of mass sits dead center in the middle of the object.
Moving right along to Section 2, torque and angular momentum. Let's see what happens when we actually apply force to make these objects spin.
Think of torque simply as rotational force. In standard linear mechanics, you push something and it moves in a line. In rotational mechanics, you apply torque and it twists. Torque equals the applied force multiplied by the perpendicular distance from the axis of rotation. This is exactly why you push a heavy door open at the handle instead of near the hinges, or why you'd grab a really long-handled wrench to loosen a stubborn nut. You're artificially multiplying your turning effect.
And that brilliantly illustrates our golden rule of torque. Greater the perpendicular distance, greater the torque. Honestly, maximizing your distance from the axis of rotation is your ultimate cheat code for generating turning power. If you want more twist, for the exact same amount of physical effort, just move your hand further down the lever.
Now, once an object actually starts spinning, it gains something called angular momentum. This is just the rotational analog of linear momentum. Just like a speeding truck carries linear momentum, spinning objects carry angular momentum. And here's a magic trick for your exams. If no outside twist, meaning no external torque, interferes with the system, that angular momentum is perfectly conserved. It stays completely constant.
You've actually seen this principle play out in the real world constantly. Think about a figure skater. When they pull their arms in during a spin, they instantly blur into a much faster rotation. When a high diver folds their body into a tight tuck, they spin faster. Even planets moving closer to the sun in their orbits speed up. Every single one of them is doing the exact same thing, trading their rotational mass distribution for speed just to conserve that precious angular momentum.
Which brings us perfectly into Section 3, moment of inertia explained. We really need to understand this rotational analog of mass because it measures an object's stubborn resistance to spinning.
These formulas right here, these are your essential IIT JEE toolkit. The tricky thing about moment of inertia is that it doesn't just depend on how heavy something is, it depends entirely on mass distribution and your chosen axis of rotation. Take a ring, for example. Its mass is spread all the way out at the edge, so its resistance is mr squared. But a solid disk has its mass spread throughout, so its resistance drops to 1/2 mr squared. Memorizing these standard values is absolutely mandatory for quick problem solving on the test.
Now sometimes, we want to simplify these complex shapes back into a single point, kind of like we did with the center of mass. That's exactly where the radius of gyration, represented by the letter K, comes in. If you wanted to compress a whole rigid body, like a solid sphere or a disk, into a single point particle, but you wanted to keep its rotational resistance exactly the same, you would place that point mass exactly at the radius of gyration. But what happens when the exam throws a total curveball and asks you to spin an object around a weird off-center axis? Well, that's when you deploy these two absolute lifesavers. To solve those complex problems, you'll shift between the parallel axis theorem, which lets you calculate moments of inertia for axes shifted away from the center of mass, and the perpendicular axis theorem, which is your go-to for flat 2D plane laminae like disks and plates. Master these two theorems, and no axis placement can trick you.
All right, let's pull back for section 4, the twin siblings, linear versus rotational motion. This is the grand analogy that makes all of this math incredibly intuitive.
I love this comparison. Look at how perfectly these concepts mirror each other. Mass simply becomes moment of inertia. Force becomes torque. Linear momentum becomes angular momentum. Literally, if you know your linear formulas, you already know your rotational formulas. You are just swapping the standard English alphabet for Greek symbols. Kinetic energy changes from 1/2 mv squared to 1/2 I omega squared. It's the exact same underlying concept, just dressed up in rotational clothing.
And this brilliantly illustrates the ultimate translation, Newton's famous second law. Instead of force equals mass times linear acceleration, we just say torque equals moment of inertia times angular acceleration. The logic is identical. If you want to accelerate an object's spin, you need to apply torque, and you have to overcome its moment of inertia to do it. See? Exact same logic, just spinning.
Okay, let's wrap this up with Section 5, Essential IIT JEE Exam Tips. We're going to translate all these theoretical building blocks into a highly practical attack plan for your exam.
When you face a daunting IIT JEE problem, do not panic. Just follow this systematic checklist. First, always identify your axis of rotation. Everything hinges on that. Second, scan the problem to see if any external torque is acting on the system. Third, if that external torque is 0, instantly apply the conservation of angular momentum. And finally, plug in your standard moment of inertia values. This 4-step process breaks the most terrifying mechanics questions down into highly solvable chunks.
Also, make sure to keep an eagle eye out for equilibrium problems. Remember that for an object, like a hanging signboard or a complex balanced beam, to be perfectly still, satisfying just one condition isn't enough. The linear forces must cancel out to 0 so it doesn't fall, and the twisting torques must sum to 0 so it doesn't spin. You literally have to satisfy both of these simultaneous conditions to achieve total equilibrium.
So, I'm going to leave you with this somewhat provocative thought. If a massive, incredibly wide, slowly spinning cloud of space dust suddenly collapses inward under its own gravity, what happens? Its moment of inertia drastically decreases, therefore, its angular velocity absolutely must wildly increase. And you know what? That is exactly how spinning galaxies and solar systems are born. So take these rotational cheat codes we've discussed today, look at the brilliant spinning universe around you, remember your checklist, and go ace that exam.